So in the previous video, we were saying that the presence of unpaired electrons in an atom is what gives something its magnetic properties. But we know that not all materials have the same amount of magnetism inherently. So let's talk about some different kinds of magnetic materials. Not all materials have the same magnetic properties. We know that these magnetic properties come about due to unpaired electrons with the same spin or directionality. And that spin or directionality gives a polarity to these atoms. So there's different degrees of magnetism. You have permanent magnets. And these are the kinds that you're probably most familiar with. A bar magnet, for example, which, as we said before, has a north pole and a south pole. When you break this in half, we said it still has, each of these halves will still have a north and a south pole, a north and a south pole, and that's because of this uniform spin or this uniform directionality. That polarity will be retained when you break a magnet in half. Similarly to a permanent magnet, we have horseshoe magnets. These horseshoe magnets are essentially bar magnets with north and south poles that are bent into the shape of a horseshoe. So these still have a north pole and a south pole. Okay, so permanent magnets, what makes them a permanent magnet is that the unpaired electrons, which we are going to refer to as domains, okay, so characteristic of a permanent magnet is that the unpaired electrons which we are going to refer to as domains, are all pointing the same way. In other words, the domains are aligned. And this is a property of the material. So if we had a little bar magnet here, let's say it has a north pole and a south pole, inside of that bar magnet there are unpaired electrons with parallel spins, which we're going to refer to as domains, and all of those domains have the same orientation. So the domains are aligned. Okay, so these unpaired electrons have parallel spins, they have the same directionality, and this is characteristic of a permanent magnet. On the other hand, there are some materials in which you can induce magnetism. So, unlike permanent magnets, there is a class of magnetic materials that we're going to refer to as ferromagnetic materials. And these are materials in which you can induce magnetic properties. in the presence of a permanent magnet. And some examples of ferromagnetic materials are iron, nickel, and cobalt. Okay, so you would notice that perhaps in these ferromagnetic materials, an example is nickel, right? And actually a lot of paper clips are made of nickel. So paper clips on their own are not magnetic. So let's just draw a little image of a paper clip. So a paper clip on its own, okay, forgive my diagram, looks something like that. And inside of that paper clip, you have domains of unpaired electrons, but they're not all facing the same way. So you might have one domain like this, one domain like this, and so on. Let's just do one domain like this. Okay, so what happens here in this paper clip is that if you bring a permanent magnet near it, these domains will actually rearrange to become aligned with the magnet. So inherently in a ferromagnetic material, domains are not aligned, so they're all out of order here, but when we bring a magnet, a permanent magnet, into their presence, they will become aligned, thereby showing we have induced magnetism. So here is a permanent magnet, north, south, and let's draw our little paper clip beneath it. And what's going to happen is that the domains, okay, if these are our domains of electrons, unpaired electrons, all pointed upward, then the domains in the paperclip are all going to reorder themselves to align with the magnet to be facing up, facing up, facing up. And now a polarity has been induced in this paperclip. What will happen then is if we have another paperclip lying around and we bring this system close enough to this paperclip, the one that has previously become aligned in the presence of the permanent magnet can now act as a magnet to get the domains in this new paperclip to align and lift it up as well. So we have induced a magnetic field, we've induced a polarity in this paperclip. In fact, it has the same polarity, north and south, as the bar magnet that we introduced it to. And once these are detached from each other, these domains will go back to being disordered like they were before.